All right, it is July 30th, 2014. This is Ben Deniston here. This is the second week of part 2 of Kepler's New Astronomy. And can I be heard out there? I'm getting some texts coming in here, or some messages.
We can hear you.
Okay, great. Okay, so this is again week 2 of 4. I'm doing a 4-week course on Kepler's New Astronomy, part 2 of Kepler's New Astronomy. The first week, last week, just to refresh, we situated defining a very specific set of observations that Kepler used to then construct his famous vicarious hypothesis model. And that becomes the basis for him to work with, and then eventually at the end of part 2 break the model in showing a very slight but significant error, which Kepler says becomes the basis of a whole new astronomy and a whole new era of science, frankly. So last week we kind of did some groundwork, defined these specific types of observations Kepler had to utilize to remove the motion of the Earth and focus solely on the motion of Mars to investigate the orbital motion of one planet. And today we're going to get into, today and next week, we're going to cover then what he does with those observations, with the vicarious hypothesis model. And the 4th week, I wanted to take some time and reflect on what Kepler does, the revolution Kepler has in Book 2, from the standpoint of Kuza's work. So if people didn't read ahead on the whole assignment sheet for what we're going to be getting into, people should know that this week and the next week, this week and next week, we're completing part 2, and then the 4th week, we're going to discuss part 2 from the standpoint of Kepler's De Docta Ignorantia. So people should be prepared to take some time to work through that, especially if you haven't worked it through before. It's not exactly the most easy read, just off the top, first time reading it through. But if you really fight through it, we have, I think, a very useful and insightful juxtaposition of Kepler's New Astronomy, getting an in-depth sense of what Kepler does, and reflecting on Kuza's methodology and Kuza's revolution, which is a certain groundwork and basis for what Kepler does with his life's work. But I wanted to start by pointing people to the last homework question, the last essay question that I assigned for the homework. And if you didn't complete all the homework this week, again, this is split over 2 weeks, so you have another week to finish the homework assignments. There's 5 assignments. If you didn't do any of those, you should do some at least. I got a handful turned in, but a number of people haven't sent anything in yet. So, but I definitely want to point people's attention to the last question, just to kind of open up here. And the last question is, elaborate the difference between focusing on a subject, say Mars, for example, versus focusing on how a subject is understood. Can you think of similar examples of a similar distinction? Can you think of examples of a similar distinction, either in practice or in need, for current areas of science or economics? And I definitely want people to make sure that they take some time to put down into thought their own words, their own insight into this last question from the standpoint of working through Book 2 of Kepler's New Astronomy. And I think, because we're not just looking at one isolated discovery here. We're getting a sense of how to think. We're getting a sense of how the greatest scientists in history thought, and getting a sense of what's the method, what's the way in which they thought, how did their mind work, why did Kepler make the discovery and not the hundreds or thousands of other astronomers that come before him? What made Kepler unique? Why did he do what he did? And it is a universal concept that we're really going for. And some people might know this, some people might not, but I think it's worth taking a second to reflect upon one of the earlier points that Mr. LaRouche really got a focus, an in-depth, serious focus on Kepler's New Astronomy as a pivotal work for the youth movement of the time to master and study. As people I'm sure know, he created the original basement rotation with Jason Ross and a few other people, brought them in. Jason did most all of the work, creating the New Astronomy site and getting an insight into Kepler's, getting an initial mastery over Kepler's New Astronomy. And part of the context was, and this is presented very clearly in a paper that Mr. LaRouche wrote in 2006 called Reanimating an Actual Economy, was drawing very explicit parallels and comparisons and cross-references to the global economic crisis, and saying, how do you take Kepler's method of thinking, and why is this absolutely necessary to approach how to solve the global economic crisis? And I think that is, I mean, Lynn has many, many brilliant papers, but that one is certainly one of them, I thought, in which he gives a very kind of clear challenge in defining how do you take the methodology and the method of thought and the quality of thought that Kepler defines and provides and gives to mankind in the context of his astronomical discoveries, and how do you apply that to the challenges of today, such as in economic forecasting, for example. So it's really a question we're fighting with here is how to think, not just what to think, as Mr. LaRouche has said in various discussions before. We're not going to change history by changing what we think. You know, we're not going to change anything by just adopting the fact that we adhere to the Copernican model, or we adhere to the idea that the Earth goes around the sun. We don't want to adhere to a thing and a thing to think about, but we need to develop and utilize and wield as a political and strategic and historical force a methodology of thought, a way of thinking, not just things that are thought. And in his discussion with some associates last night, I think Mr. LaRouche also emphasized a very similar point, just looking at the similar implications, looking at the current world crisis, and just putting on the table a very clear and stark challenge that this whole thing is breaking down. The whole global economic system is breaking down. The BRICS nations are doing the right thing. They're moving in the right direction. South America is moving in the right direction. Where the hell is the United States? And who in the United States actually knows how to run an economy? And how, if the lives, the 300 million plus lives of the United States are put on their shoulders in the context of a breakdown of the entire financial system, literally chaotic implosion of the financial system, who actually has the capability, the scientific know-how, to competently put into place the right types of measures when literally millions of lives depend upon your actions, and your actions being right and accurate as you take them. So from the very beginning of the strong emphasis on Kepler's work, starting in around 2006, Mr. LaRouche had talked about Kepler much farther into the past, into the 80s, the 1970s and 80s, It was a big part of what he was doing with the Fusion Energy Foundation at the time. But starting around 2006, when there was a renewed emphasis on mastering Kepler's original works, it was always in the context of developing a leadership in terms of the highest method and capability of scientific thinking that's needed to lead the world. And so, that is what defines the intention for these classes. That's what defines our scientific program, is developing that quality of competent leadership. So, given what Mr. Lewis was saying last night, I think it's worth just putting that out there to open with. Returning to this question again, elaborate the difference that I want people to really take some time and work through after completing the previous assignments. What's the difference between just focusing on a subject versus focusing on how a subject is understood, how you even think about a subject, how you define a subject? Can you think of other examples? Well, I think, Lynn definitely gave us one yesterday in reference to how do you define value as a scientifically defined actual physical economic scientific concept, not just arbitrary price value or something. So anyway, I just want to put that on the table as some of the context in which people should be, the context that should govern people's minds as they're working through this material. And I think the best thing for today and these Wednesday sessions is a lot of interactive dialogue regarding the work people did over the week between last Wednesday and today. I can take some time and go through things, and I can go through things that people have questions about. But I would rather just open up, because it helps me and it helps the class overall, I think, if I get a sense of exactly what people are thinking, what problems they're running into. As wonderful as Google Hangouts are, it's not the same as actually being in the room with real people and talking to real people and seeing real people. Some people have very nice icons there for their avatars or whatever you call them. But it's, I think in terms of what we want to get out of these classes is the best is going to be people putting on the table what thoughts they have, where they're having trouble, what they understood. And so from that standpoint, I would actually like to open up just by asking people if anybody can answer the first question, maybe get a few answers on it, of the assignments that were given for this week. And I can pull that up if people don't happen to have it right in front of them. I think I can pull it up. All right. So again, last week we took a lot of time, and Kepler takes a lot of time getting these observations and measurements that he's going to deal with, getting them absolutely precise, as accurate as possible, in order to use them to do what he does for the second half of part 2. So I'd like to open up just by asking if people can answer this first question. Explain how Kepler uses his corrected acronical or opposition observations to develop the construction in chapter 16. Why does this define specific values for the sun, the observer to center distance, and the center to equant distance?
I have no clue. They clearly like no fucking idea on that whatsoever.
Here is a picture of the model. Maybe if this isn't totally clear yet, I can step back a couple of steps and remind ourselves of what we have to work with here. Kepler developed this table of opposition observations from Tycho Brahe's data. And he takes the time to convert Tycho's observations from opposition with the mean sun to opposition with the actual apparent physical sun, and including making other various corrections and adjustments and making sure everything's precise along the way. Then he selects 4 of these opposition observations. And here we have a nice animation from Jason's original website showing this series of opposition observations. So here you obviously have the sun, the Earth's orbit's in blue, Mars's orbit's in red, and you can see every time the 3 of those bodies line up, a line is drawn where they line up, and you get an opposition observation. These then allow you to know to, in effect, remove the motion of the Earth and focus solely on the motion of Mars and Mars's motion around its orbit. So we could now know on 4 specific dates where the sun saw Mars, in what position of the sky the sun saw Mars. So we will remove all the artifacts of the fact that we're viewing from the Earth, which can cause all types of variations and irregularities, and have a set of observations of how the sun would see Mars. Those 4 there. So we know when they were, and we know where Mars was seen. Now, last week we took some time at the end of the class to kind of fight with the last column of the table, in which Kepler defines what you see animated here. So now, remember, this is our equant. This is our point of uniform motion. So, in effect, it's a very, very slow clock. You're assuming there's some point of uniform motion, some point at which equal angles and equal times are traversed. So if that point exists somewhere, if you were standing at that point, you'd be watching Mars moving uniformly. So what that means is if that point exists, then we could take the time between each of these measurements of the opposition and define a direction where the equant would see Mars at that time. We're about to see this next one come up here. So we know that because we know the time difference between this opposition and this opposition, then we can just turn that time into an angle and develop a series of relative angles, times between these opposition observations. So I assume that's clear for most people. If there's at any point in this, if there's questions or lack of clarity or points of emphasis, people should just certainly speak up. But I would like to see if anybody, so kind of with this refresher, so I've given you the first answer. I'm a very generous person, apparently. So we looked at
He's benevolent.
we looked at how Kepler uses these corrected opposition observations. Well, the first half of the first answer. Can you explain how he uses these observations to develop the model, the construction he does in chapter 16, the vicarious hypothesis construction?
You're shaking your head, yes?
Maybe.
Get up there.
How best to formulate it though.
Go for it. Classic.
Alright. Can I be heard?
You come up here if you want.
I don't know about that. Yeah, but it's. Okay. Well, so I mean, the way I'm thinking about it is, the two things that you can discover in terms of the orbit of Mars is, where if you're at the sun, you have 4 different observations in terms of where Mars is positioned in the sky, and so you have, and you also have the equant, because you also then know how long or how much time has passed in between each observations, so you sort of know, you don't really know where that equant point is, but you do know the relative angles. And so what Kepler does is, because in order to form a circle, you need at least 3 points, G, D, and E. You need at least 3.
Look at some of their animations too if you want.
Yeah, that's a bit.
Do you want to look at?
No, I have it in my head. I just don't have the words.
Right. So these are the angles we're talking about, right?
Mm-hmm.
Well, Jason was very nice to give us this great animation that really communicates a lot, but it's worth, I think, being sure you know exactly what is happening here and what you're doing with this this kind of interactive expression of the types of calculations and adjustments that Kepler was dealing with.
Well, it seems like he takes the set of calculated time measurements and what that would imply as to what the equant would have seen at those time measurements, and turn that set of data for time into basically a set of data to be used for observations. And so he takes the set of lines which represent the locations, the relative spots in around the equant's center at which the equant would have seen the planet after the time had passed between one observation at opposition of Mars and a second observation. And so he knows that these are going to have to intersect with the lines of observation that were measured by taking the actual measurement as opposed to just calculated. So he has to reconcile this, but then the question is, well then, but you can make the lines of observation intersect in an infinite number of different ways.
Mm-hmm.
But the reason he has to make them intersect in that way is because he has these rules which he's trying to fit the model into. And one of the rules is that the planet is traveling on a perfect circle. So that's one constraint that he has to fulfill. And so if he makes the sets of observations intersect at points which all lie in a common circle, then he's fulfilled that constraint. But then he has another constraint, another parameter which he has to fulfill, which is that the center of the orbit has to lie on the line of apsides. And so he, specifically on the line of apsides in between the Sun and the equant. And so by trial and error, he basically finds as best of a fit as you can get, and that's how he does it. But it was important for me to think that, you know, the only reason the equant even exists is because he's making it exist.
Right.
And if there was an equant, then this is what it would see. Now, given what the equant would see, and given what we've actually measured to be seen, how do we combine them to make a model which fits these two parameters here?
Yeah, exactly. Yeah. So you're starting with these basic assumptions that, as you just said, the equant exists, which is an assumption, and you have perfect, the orbit lies on a perfect circle, which is an assumption. And like you're saying, if you assume the equant exists somewhere, we have these relative angles between their positions, and we could, as it's expressed in this animation, position the equant such that if the equant was right here and angled it this way, and the Sun was right here, then we know that for that observation, for this observation that both the equant and the Sun were looking at, Mars had to be at that point of intersection. That's where Mars would have to have been for the equant to be right here, oriented this way, and for the Sun to be right there. But if we position the equant like this, we can. Sorry. Oh, am I wrong? Computer here. Say we step back to having starting with just 3 observations instead of the 4. So again, if we had positioned the equant right here, and the Sun, and it's angled how we have it now, rotated how we have it now, for each of these 3 observations, they intersect at one point. So for each of those observations, that's where Mars must have been if this was actually the position and orientation of the equant relative to the Sun. Any 3 points, as part of your geometry homeworks, any 3 points defines one and only one circle. So this would define, this positioning and rotation of the equant would define this specific circle. But we see that the center of the circle does not meet the criteria that Kepler uses, that Ian was just describing to us, which is that it has to lie on the line of apsides going through the Sun and the equant, and it has to lie on the line of apsides in between the equant and the Sun. So by people can see down here, we have a clear description of exactly what the motion of the mouse does when you're playing with this animation. It's actually not just to piss you off, although when you're using the mouse in this animation, it kind of makes you do that. It can be very counterintuitive if you're trying to get it all to line up. But we see here it clearly says the horizontal motion changes the direction of the line of apsides. So you can see here, as I move side to side, the angle of that line connecting Mars and the equant is rotating. So the whole line of apsides is rotating. And as a function of that, you can see that the circle, the orbit would move around, and it gets larger and smaller as a function of that. And the vertical motion addresses another thing we were discussing last week. The vertical motion rotates the equant, as you can see here. So notice the line of apsides is no longer swinging back and forth. It's pointing in the same direction. But now the equant is actually twisting, rotating back and forth, which is because we were discussing some of this last week. With the measurements of the time, all you really have are the relative times or relative angles between different observations. But just from that alone, it's not clear where you start counting from. So when we're rotating the equant, you're changing, in effect, where you're counting from. Hoping that makes sense. So if you take 3 observations, you can fulfill these criteria with the orbit being on a perfect circle and the center of that circle lying on the line of apsides in between the sun and the equant. And you can actually do it in an infinite number of different ways. You can find a whole array of positions where you can place the you can position the equant such that it lies somewhere in this line of apsides. Now, Kepler notes that Ptolemy and I believe Copernicus had just assumed that the eccentricity here, this value was bisected by the center of this circle. So just by this construction, if you just start with these observations we're dealing with, and we're trying to define what the orbit is, where the equant is, how it's positioned, to fit these observations that we work so hard to make sure we're as accurate as possible. If you don't assume that the eccentricity is bisected, then it can be anywhere along here. So you can find the center of the orbit. If you assume that's bisected, you just have one position, and you can just solve it there. So here we have 3 observations which intersect on one perfect circle between the equant and the sun's observations, and they the center of that orbit lies on the line of apsides in between the equant and the sun. What happens right now if we add a 4th observation, which Kepler works with? Can anybody explain why we have more circles now, and what's going on between with operating with 3 observations, three oppositions and 4 oppositions.
What's the gray circles towards the middle? That's the center of each orbit.
Well, each circle represents. Am I able to be heard, do you think?
Yeah, I think so.
Okay. Each circle represents the relationship of 3 points on each circle, but not for the 4, just for 3.
Right. Sorry, I'm just being messaged here. Right, so you have 4 points of intersection. If you take any 3 of those, you define 1 circle. So we could take this one, and this one, you get 1 circle. Take this one, and this one, you get a different circle. Right. So you have 1, 2, 3, 1 circle. 1, 2, 3, 2 circles. 1, 2, 3, 3 circles. 1, 2, 3, 4 different circles. And we can see they don't all line up, so the observations don't agree with each other. Sorry. So what we have to do then is
what was he able to measure the radius from those 3 previous 3 observations?
It's all in relative values. He sets the radius. He'll set, if he's measuring from 1 circle, 1 orbit, he'll set that radius as 100,000. It's kind of an arbitrary unit to start with, and then measures everything relative to that. So if it's half of that radius, then it's 500,000, just because you started with 100,000. You could have started with 1, and then it would be 1/2. So it's just a measure of the, just picking kind of a unit to start with. So we have, Kepler adds this 4th observation, and what it does is it creates a construction that he has to kind of take a series of iterative steps to determine the orientation of the line of apsides and the equant, the position of the equant more or less, such that all 4 of these circles line up on 1 circle, and the center of that circle lies on the line of apsides. I'm not.
Oh wow, that is the most perfect that I've ever seen it.
Looks nice. The one thing I just was wondering about, Ben, is, and maybe I think you might have just gone over this, but I think it went one ear and out the other. Why is it that that Kepler's predecessors, the ancients, so-called, only needed? Why is it necessarily true that because they employed this bisected eccentricity, that they only needed 3 measurements as opposed to 4 without the assumption of that bisected eccentricity? That's just one thing I'm not quite clear on.
Well, it can be in a simplified way for us just to see it. It's illustrated in the animation here. We could take some time and look at the mathematics involved behind the animation, but that I think would take a little bit more time, and I wouldn't have that right off the top of my head. But just taking these 3 observations, this animation is basically just doing a bunch of the trigonometry calculations for us that we would do to define this otherwise. And we know if we have these two sets of 3 observations, we know they're going to intersect at 3 points. So we know it's going to define one and only one circle. And as we move the equant around, we can see clearly that that circle can kind of move around, and the center of that circle can move around and can align itself on various points of the along the line of apsides in between the sun and the equant. So, the animation is an expression of real-life interactives, doing all the math for you real quick. But, yeah, it helps to sit down and actually go through the calculations and get a better sense of exactly why that's the case. And that would be a good assignment for people to do, to sit down and go through. But then as we saw, so then if three can make it so you could put the center of the orbit anywhere along this line of apsides and would satisfy the requirements, then the only way you could determine one orbit, instead of just arbitrarily choosing any one of an infinity of orbits which all satisfy the requirements, is to define some additional criterion, which was the assumption that the eccentricity is going to be bisected, that the center of the orbit is going to be exactly in between the equant and the sun, which we can see here is not the case for this solution with the 3 orbits. But then, as we were just looking at, when you have the 4 orbits, or the 4 observations, each set of 3 observations gives a different orbit. And so you have to kind of plug in a value for the equant, see where all the points intersect, and see if those define 4 different circles or if they all define the same circle. And if they define the same circle, you have to determine if the center of that circle is on the line of apsides or not. And we can see it in the animation, which expresses all the calculations going on behind it. But off the top of my head, I couldn't say exactly why, in terms of the fundamental mathematics of this geometry you're dealing with, why this defines one and only one eccentricity specifically, other than you can see it clearly expressed in the animation here.
I know there was plenty of observations too, the chronicle.
Mm-hmm.
Like, I know he just did 4, but like, why didn't he just do all the ones he had available to him and apply it with 1? I mean, was it too much work at the time for him, maybe, or 20?
Well, then you'd get, if you had 12, how many sets of 3 combinations are there with 12? You'd have a lot of different circles, because if you had 12 observations all at once, then you'd have 12 points of intersection, and then any set of 3 of those gives you it'd be a lot more calculations. And I think this was already very tedious enough to do by hand at the time. But this is enough for him to define one orbit, one eccentricity, one position for the eccentricity for the orbit of Mars. Again, operating within these assumptions that the equant exists, that the motion is governed by a point of uniform motion, and that the orbits operate on perfect circles. So are people kind of clear up to this point? Could people explain this to someone else? Does it make sense what Kepler did? Is it just a, no pun intended, flashy animation that just moves around and it's fun to play with? Yeah.
Well, it makes more sense now I just said it just makes more sense now that because I was a little confused also on what Ian was asking. That was my same question.
Mm-hmm. Okay, well, let's
That makes sense. It's helpful. Yes, thank you.
okay. Again, this section of the book we're splitting in between 2 weeks, so let's look at a couple more things here, and then go on to, and then see if there's any more questions or discussion, and then can go on to next week. Here's another good one I'm going to throw out to people. So Kepler makes this model, this vicarious hypothesis. He basically takes these observations he's working with and kind of adjusts the position, orientation of the equant little by little until he gets something that, an orbit that lines up as good as possible, the best possible. Well, hold on, we got being told New Jersey has a question, but they are not allowed to speak for some reason.
They're not allowed to speak. Can't talk.
Hmm?
I said they can't talk.
They're reconnecting. I don't know if it's because you muted them or what, but they're reconnecting.
Okay. All right, I think we can hear you guys now in New Jersey.
I'm having some trouble here. Okay, can you hear us, Ben?
Yeah.
Okay, there we go. Hey, can you join that? Okay, here's Courtney.
Hey, Ben.
Hey.
I just didn't really, I really didn't understand how, because Kepler doesn't make the assumption of the bisected eccentricity that he needs, I don't know where he gets, how does he know he needs a fourth point? Like, how does he go from 3 points to 4 points? Because he doesn't make that assumption.
Given the time and the context of this class, I think it's just most clearly expressed in the animation here, where you can see that when you have only three observations you're dealing with, you can clearly get a number of positionings of the equant where you can get one orbit and the center of that orbit to lie directly in that point of eccentricity.
Ben, one way Alan was explaining it to me here, which was helpful, is that he was saying that, you know, basically just going back to fundamentally what you're trying to do, you're trying to reconcile the hypothetical existence of the equant with the observations. And if you're only using 3, then any orientation, any different orientation of the lines of observation that you can come up with, there's an infinite number of them, all of them will create a perfect circle. So you will satisfy the requirement that you have an orbit around a perfect circle with an equant, which satisfies the reconciliation of the observed positions from the equant and the measured positions of the orbit. But there's so many of them, how would you know which one you would choose? There's an infinite number, and so you would basically, if you just said, well, it's the one single one at which the center of the circle lies at the in between in the middle of the line connecting the equant and the sun, the line of apsides. But then if you don't make that assumption, then you're in a situation where if you don't make the assumption that it has to be on the exact center of the line connecting the equant and the sun, then there has to be some other parameter which enables you to fix it at a single point, as opposed to just choosing arbitrarily from an infinite number of different places it could be. So the question is, how do you fix it at a single? How do you, given a set of do you have enough parameters? Whether it's parameters or observations, do you have enough to combine your whole building material into one single orbit, as opposed to having a different number of orbits which could satisfy your requirements?
Yeah, right. So it's like adding an additional constraint to the very kind of variabilities you're dealing with, which constrains it down to one point instead of this infinity of options here. So Kepler he defines this vicarious model, and he finds, based on utilizing these observations, what's the best positioning and orientation of the equant I can get that seems to satisfy this the best possible. Boom, there it is. So now he has this model, and he then says he tests the vicarious hypothesis against the other 8 and all 12 of the opposition observations that we developed last week from reworking Tycho Brahe's data, his opposition observations. So who can explain what it means to test one of these other opposition observations with the vicarious model? Hopefully that's a clear question. It's open to our live audience here in Percival also.
You're talking about those points down there, any 4 of those?
Yeah, well, he, remember in our table we were working with, we had 12 opposition observations. So we have 12 very precise observations of when, where and when the sun would have seen Mars at 12 points. These 12 of these different years here. He takes 4 of them, which have been underlined here, to construct his model. He builds a model. The model is basically a positioning of the equant relative to the sun and the line of apsides, and the center of the orbit relative to the sun. And so now he has a model, and then he says he tests that model against the other 8 of his observations, which are places where the sun would see Mars. So who could describe what that even means? How you would, what that means to test one of these other opposition observations using this vicarious hypothesis model he developed here?
Yeah, I mean the whole point with the vicarious hypothesis is to find out where the equant is, and so if you go back down all the different dates, Kepler knows when all these observations were taken and how far apart they were. And so it's sort of just like, say, 1597. You sort of wind the clock in terms of the equant, 2 years or so, and so you know where the equant sees Mars in 1597, and you also know where the actual observation is, or from the sun, and you see if they line up correctly. And I guess it's only off by 3 seconds.
Mm-hmm.
And you do that for every single one, and it turns out they're pretty close. So.
I'm assuming you guys could hear that. So just to illustrate what you just described, so 1597, that was an observation after the 1595 one, right? So here, if we just wait a second, we can see. So this is the first one he used, the first observation he used. I forget exactly what the years were, but the ones that were underlined down there. Second one, anyway, the third one comes here, and the fourth one comes here in that position. The third, and then the fourth. So that's this one here. Assuming these are all oriented the same way. So that's the 1595 observation. You said was this one right here, assuming the orientation has stayed the same through these. So say this is the 1595 one. You can calculate the months, days, and hours of time elapsed between this observation in 1595 and then the observation in 1597 that we just discussed. So you have how much time elapsed between them. So you could basically just let that time run on our clock, our equant clock. So 2 years and whatever time it is, we could look back in the table in the book and see the exact. This is another thing that's just a good exercise to do. Go to the table, how many days exactly have elapsed between the 1595, is that what it was? 1595 and 1597?
Yeah.
Yeah, 1595 and 1597 observations. Then convert that time into an angle for the equant. That's our clock moving uniformly over that time. And then so this model will then give you a direction that the equant would see Mars at some point in the future. Now we picked a point in the future where we have an observation that's actual data. And so we can compare that with what this model gives. If this model says the equant sees Mars in this direction here in 1597, could do a little trigonometry and calculate where the sun would see it at that point. And then we can compare, what does this model tell us about where the sun sees Mars in 1597? And now, wait a minute, we actually have an actual observation of where Mars was in 1597 by opposition, where the sun would see Mars then. So we could compare what the model predicts or forecasts or hindcasts or whatever you want to do. You can go forward or backwards to test it. And we could compare that with what the actual observations we have available are. So it just people, we should actually know what it means to work with the model, how these models work exactly. You take the time, apply it to the equant, gives you a direction of a line of sight from the equant. Do a little trigonometry, and then you can determine a line of sight from the sun. And that's how you use the model to forecast Mars's position at certain given times. So what Kepler has here is then he compares what the before he does this, he also includes consideration of the motion of the line of apsides, which is a factor that he's aware of and has to take into account. So it adds kind of a slight motion of rotation of the whole orbit. So over so many years, you start to get a few minutes variation because the whole orbit's been rotating a little bit. So he takes that into consideration. And then he's able to use his vicarious hypothesis model to test it against these rigorous oppositions. And what do you see? You have less than a minute, a minute and a half, way less than a minute, 2 minutes, a little bit less than a minute, 14 seconds, 3 seconds, 18 seconds, a minute and a half, 27 seconds. So the big variation in all of these is about 2 minutes. So this is an incredibly accurate model that he's just developed here. He's just developed an incredibly accurate positioning of this equant, this point that governs the motion of the planet according to the model, and the size of the orbit and all the positionings to give something that forecasts where Mars is on its orbit better than anything that had been developed up to that point. And I think that would probably be a good place to pause for where we're going to go today. And I think hopefully people will maybe have some more thoughts or questions, considerations on what we've gone through so far. And next week we can cover the second half of the second half of part 2 of the second part. And we can look at how he then comes back and tests this vicarious model with a completely new method, which is where we get to the real explosive part that shatters astronomy up to that point. And again, I think we'll again emphasize the importance of the homework questions and work. Because again, going back to what I was saying in the beginning, you know, this is critical in developing a capability of thought, of insight. And we have an opportunity to have Kepler take us through his process of discovery. And for people to do that, you have to, I mean, the group work is important, these classes are important, but me here babbling at you over the screen is not going to give you a discovery necessarily. It's going to require some personal work to sit down and think through and fight through your own thought process and trying to take your own mind, your own thought process through the steps that Kepler went through and actually create the same geometry, the same ironies, the same challenges in your own mind, that you'll really begin to make some discoveries and figure things out. And as was presented in the beginning, leading to more broader general shifts in methodology and ways of thinking about science and politics generally. The intention is to learn how to think. So I really want people to focus on the homework, and especially the I think this last essay question I posed here I think is a good thing to play with, and people should just try and have fun with it and really try and conceptualize the gestalt, the single insight into what Kepler's doing in part 2, and then think about it from a more general standpoint of how that can be applied in various analogies or other ways to other questions, other considerations. It's a useful type of exercise that I think people should really take some time with. So that'll be this next week, but is there any more questions or thoughts or complaints? I'm sure Ray's got some complaints.
I actually did have a complaint. I went to LaRouche Pack, then I went to Science, and I went to Book 2, and it said coming soon.
Yeah, there's 2 sites for the new astronomy. There's the one that Jason made in 2006, which says it says old site on it. Here's a Science.LaRouche Pack. Oops.
Yeah, if you go to Book 2. Oh.
Yeah, well here's this is a new site that he started, which he finished Book 1 for, but that's all he's been able to do so far. So Book 2, Book 3, Book 4, Book 5 aren't there yet for this new site, the new astronomy. Here's the old site. This is what we've been working off of, which has all of it there, Book 1 through Book 5. So since we're on Part 2, you can go here. If you want a refresher on Part 1, go to the new site. Any other questions or thoughts out there?
Oh, Ben, just on the homework on question 3. Were we supposed to use a particular length for the radius of the orbit? Because there's none is listed there, and I just used the radius that I calculated from the question 2. Okay.
Yeah, just 100,000.
Oh, okay. Okay.
Because here we have the eccentricity values given here.
Right.
Are given relative to 100,000.
Oh, I see. I guess we should have gathered that from calculating from step 1. When you find it relative to 100,000, it's a similar number to that. So okay.
Yeah, there's just a few. Some of the steps get a little. You got to keep in mind where your units are. Keep an eye on your units. The previous worksheet, you start with the idea that the Earth's orbit is 100,000. Then you calculate Mars's eccentricity relative to the Earth's orbit being 100,000. And then the last step is then convert Mars's eccentricity in a metric where the Earth's orbit is 100,000 into Mars's eccentricity in a metric where Mars's orbit is 100,000. Simpler than it sounds when I say it like that, but yeah. So here it's 100,000 for the radius value here.
It's muted. Oh, I guess it's not.
Was 100,000 what other astronomers used as well? Is that pretty like?
That's a good question. I would guess so, at least around the time that Kepler was working. But yeah, I don't know. It's a good question.
Can you hear us now?
Yeah.
Okay. Well, I'm just trying to pull this around and conceptualize it from the standpoint of Kusa. As it seems to me that, and to try to think about what Lynn is saying, what it was saying, for example, a year or 2 years ago, when he was focused on, he kept on going after the vicarious hypothesis. And this is, and in a sense, it's a it's a rigorous use of the method of learned ignorance, right? Because he begins with an hypothesis about what's really causing the motion of the sun. Am I right that he starts there, but then if he wants to make any progress on figuring out that hypothesis, first he has to figure out, what is it that we don't know? What is it that the current models fail to account for? And so he's seeking constantly a way to isolate variables so that he can come to paradoxes. And when he gets those contradictions, then he can work from that and define something. Anyway, that's what we're coming to. We're coming to this great climax in the work where he exposes that it totally falls apart, right? Anyway, can you say something on that?
Yeah. Let me start with this quote here from. Let's see. Well, I think it's the quote 254. Just give you one kind of taste of it from Kepler's own words. There we go. So he says, at the same time, however, it is not unusual, whether in geometry or arithmetic or in dialectic, to use a form of argument which leads to an absurdity, so that if something absurd is seen to follow from the assumptions, they are rejected as false. And this is carried out until the consequent removal of excess and defects unveils the exact truth, which in the mathematical disciplines is a mean between the two. In the present case, this comes about in the following manner. So kind of jumping ahead from what I've gone through so far. So if we can follow certain assumptions in a logical reasoning, and we can rigorously show that they lead to an absurdity, as Kepler discusses it there, then we can define a basis for knowing we can reject those assumptions. And this is very clear an example in Plato's writings. His conception of the Socratic dialogue, I think, is a very similar process. This whole book is really written as a Socratic dialogue. Kepler is trying to, it's literally the exact opposite of the crap people get today in school with Kepler's 3 laws. You're given these 3 formulas, and that's what you're given. Kepler doesn't give you 3 formulas. He gives you a step-by-step process for you to go through to lead your own mind to follow logical steps and follow them to their own contradictions, their own absurdities, and then go through a process with him of hypothesis and testing of hypotheses to try and discover a higher order principle which was outside of any of the initial assumptions that you started with. So I'm hesitant about getting into too much of exactly how Kepler does it because of the time, and want to cover a little bit of that, kind of focus on that a little bit more next week. But it is very much of the method of Cusa, of the method of Plato, in terms of taking you through a process of defining a contradiction. And we were discussing some aspects related to this in the basement some last couple of weeks or so, and one thing came to mind is that it's there's a lot of absurdities in current cosmology, for example. Cosmology is just crazy. It's just nuts. They don't know what the hell is going on with all these things. There's so many. I literally just saw a new paper which says that, which posits the idea that black holes might all of a sudden turn into white holes and explode. And that might be a way to explain these very energetic, intense, active explosions of stars that they see. There's just all these cases, just totally wild speculation, theory. The theories are constantly being overturned. Dark matter is created to account for certain things. Don't know what it is, but it's created anyways. Dark energy is a whole another crazy thing. There's real anomalies that are there, and it's very easy to sit back and say, well, this is all crap, it's crazy, doesn't make any sense. But to use the reference that we're going to get into next week, where is our, how do we define an 8 minutes of error in current cosmology? How do we actually define, how do we rigorously define and isolate and nail down a contradiction or a series of contradictions which can demonstratively and provably overthrow certain hidden assumptions or hidden beliefs which have been holding back the falsely constraining the entire dynamic of thought about cosmology or astrophysics or astrophysical processes today, to use one example. If Kepler didn't go through this process of defining the vicarious hypothesis, testing it the way he does, and finding the contradictions the way he does, he doesn't really have a basis to know what to throw out, if it can be thrown out, and you don't take your mind through the process of fighting through the contradictions, fighting through the process of defining and identifying the contradictions, which, as we're seeing here, is more difficult than it's an actual serious process to find an absurdity, to find a contradiction. That then becomes, those contradictions then become the substance, the stepping stone, the liftoff point to then begin to hypothesize about higher level causes. And I think we'll probably save it for 2 weeks from now to discuss more of the specific implications of the particular assumptions that Kepler's dealing with, and the way Kuza had earlier treated those specific assumptions, where they come from, what they mean, because it's not just any assumptions he's dealing with, but they have a very particular quality which is worth identifying and reflecting upon. So that's some short aspects of it, but there's certainly a lot more that can be said. And Jason's video on metaphor, she did it's on the LPAC site, is also a very, very good, excellent addressing of this specific subject we're dealing with here. It's another thing I could probably, now that it came back to mind, probably add it to the homework list even. It's another thing for people to maybe look back at after we finish the towards the end of this series on part 2.
Yeah, just to follow that up, can you hear me, Ben?
Yeah.
With the present strategic situation, and to conceive of what LaRouche's method has been up to this date, and the way by which we have, as a movement, as a force led by Lin, laid on the table for people, well, here's what's going to happen to your system if you define it according to these axioms. And we've reached a point now, which is if you're conceptualizing why Lin is saying we're so much stronger with the allies that we have, with South America, with China, with Russia, with India, it's worth considering. You think about what the Chinese representative from the economic think tank, the state economic think tank, said, Ding Yifan, at the LA conference, which was effectively the Chinese in the 1990s, they were perfectly happy to accept the idea that money is inherently valuable because they were making money hand over fist from slave labor policies, from a coastal economy with, and the middle of their country was choking to death, and people were, being used in sweatshops and so forth. And Lin and Helga and this movement continually said, this is nothing but smoke and mirrors. This is all dross, and it's all going to collapse. And you cannot have an economy on that basis. Money is just an illusion. And the fact that now we're in a period where over the past 15 years, there's been a growing and growing reversal of that, and a commitment to high technology, high wage development, as expressed in the New Silk Road, as expressed in the BRICS summit. I mean, we should just consider that, because that's, for example, I'd be interested to know what was the response. I'm not sure I'm familiar with what was the response to Kepler's breakthrough. How long did it take for this to be? Surely it made a huge splash immediately, but what was the overall response? Who held on to the Copernican? Who held on to Ptolemy? Who held on to the lunacy? And what additional work was done to get people to shift? Because we're in a different moment now, where these nations have shifted. And again, I think that puts this point on the 4 laws, and that puts the point on a new series of conferences, of international conferences, is that Lin's method has been proven. This is not in a positive way, not just in a negative way, by the great achievements of these nations so far. And and there has to be, to bring to bear upon all of this the question of energy flux density, a rigorous understanding of a fusion economy. It completely has a totally different power today than it did 40 years ago, because of what we've done in the interim and because of what's been proven from Lin's method.
Very well said. It's a good point to end on. We should probably give people a few minutes to prepare for any additional activities they have to do tonight.
Hey, Ben.
Yeah?
Just real quick. One idea we had here in Seattle as to why Kepler uses 4 instead of 3 is because the quadrilateral can only lie on one circle, whereas if you have a triangle with 3 observations, you can have multiple circles. So all the observations wouldn't lie on one center. You need a quadrilateral to have all the observations lie on one center. That's just one idea.
I think we can do, just because it's come up a few times. I can talk to Jason and we can go back and look more directly at the calculations Kepler goes through in chapter 16 and maybe define a worksheet or a pedagogy sheet that gets at more directly the geometry involved in defining that. Probably a worthwhile thing we could pull together in the next couple of days or so and make available. It's probably one of the things you just have to sit down and work through. to get a sense of. So with that, I think we should probably cut off now, about out of our time here, and I will again emphasize the homework is critical to understanding and personally understanding what Kepler did. And the ones I've gotten have been good and enjoyable to read, and it helps a lot to get a sense of what people are thinking. So I look forward to receiving more, and I will see you guys next week.